Hello and welcome back. In this video, we're going to combine the relationships that we saw from Charles' law, Avogadro's law, the Guy-Lussac law, and Boyle's law into the ideal gas law. We will then use that to make some calculations of systems involving gases. So the ideal gas law incorporates these relationships that we've already talked about. If we take Boyle's law, which looks at volume and the relationship between volume and pressure, if we take Charles' law, which involves volume and temperature, and then Avogadro's law that looks at moles and volume, we can combine these all into one relationship, and we call that the ideal gas law. The fourth relationship we talked about earlier, Guy-Lussac's law, we see is somewhat redundant in this sense because it involves pressure and temperature, and we already have the relationships described here. So when looking at Boyle's law, again, we can relate volume and to pressure, and we did that by holding the moles and the temperature constant. In order to make an actual relationship, and not just as an equality, we need to have a constant. So we're going to use what we call the gas constant R. This gas constant R is similar to what we saw already when calculating the root mean square speed for gases at a given temperature, but it does have different units. And so what we see here is that there is a relationship that exists between each of these variables and that we can combine them all together to get the ideal gas law. Because of this, we don't need to memorize Boyle's law or Charles' law, or Avogadro's law, or the Guy-Lussac's law individually, but rather we need to just know the relationship as we see here. So let's see if you've understood these relationships. So let's say that we have pressure, gas inside a rigid container, and therefore the volume is fixed. We measure the gas, or we measure the pressure as gas is added to the container. And so then we plot the pressure as a function of the moles of the gas, temperature being held constant. We want to know what variables best describes the slope of this line in the plot. Pause the video and try and determine this on your own, and then come back and we'll talk about it. Welcome back. So as we saw already, according to the ideal gas law, pressure times volume equals moles times the ideal gas law constant times temperature. In this plot, we're looking at pressure as a function of moles. So if we rearrange this equation and set our y-axis value as pressure and our x-axis as moles, then we can see that the other variables that are left out are the ideal gas constant R, temperature, and volume, and that is our slope. So that, again, pressure is the y, x is the number of moles, and then our slope is the combination of the constant, temperature, and volume. In order to do calculations involving the ideal gas law, we need to become familiar with some common phrases and ideas. And we talk about standard state for gases. We talk about standard temperature and pressure. So when we talk about standard state conditions for gases, this is referring to standard temperature and pressure, also known as STP. And that's when our system is at 0 degrees Celsius and the pressure of the gas is 1 atmosphere. So let's say that we have a balloon filled with helium, where the volume is 1 liter, pressure is 1.5 atmospheres, and the temperature is 5 degrees Celsius. What will be the volume of the balloon after half of the atoms of helium leak out? The temperature is raised to 10 degrees Celsius, and the pressure is reduced to 3/4 of an atmosphere. Okay, how do we do this? Well, we know that there's a relationship that involves pressure, volume, moles, and temperature for ideal gases. We can rearrange this relationship and set it equal to the constant R. Now, why would we do this? Well, we're trying to talk about the system, our balloon with the helium in it, changing over time. So we need to talk about initial conditions and final conditions. So we can say that our initial conditions are going to be equal to the gas constant R. Because this is a constant, then the final conditions are also equal to this gas constant R. And now, since they're both the initial and the final conditions are related to the same value, we can set them equal to each other. At that point, since we're solving for volume, we do the algebra necessary to rearrange this equation, and then we can plug in the values. Our initial pressure is 1.5 atmospheres. The initial volume is 1 liter. Now, what about the number of moles? Well, what we know is that half of the moles have left. So our final number of moles is going to be 1/2 of the initial. It turns out that it doesn't matter exactly how much it is. It's just the ratio of those that we need to account for. The temperature is 5 degrees Celsius, but when we're dealing with gases, we always need to deal in temperatures of Kelvin. So we need to add 273.15 to the values. Our final temperature, therefore, would be 283.15. Our initial moles is just N1. Our initial temperature is 5 plus 273.15, or 278.15 Kelvin. And then the final pressure is going to be 3/4 of an atmosphere. What we see here is that our units of atmospheres cancel out, our units of moles cancel out, and our units of Kelvin cancel out. And we're left with approximately 1 liter worth of volume. Now, why did this happen? Because didn't we change our different variables? We did. But because we changed multiple at once, and they each had different effects on the volume, decreasing the pressure would increase the volume, increasing the temperature would increase the volume, but decreasing the number of moles would decrease the volume. So it turns out that they actually balanced each other out. Okay, here's another problem for you to do. Determine the volume occupied by 1 mole of gas at STP. I've given you here values of the gas constant R, and you're going to need to think about the units that are involved in order to determine which gas constant R to actually use. So pause the video and try this on your own. Welcome back. So how do we solve this? Well, we need to remember that when we're talking about STP, that's referring to a fixed temperature and pressure. Because we're solving for volume, we need to rearrange the ideal gas law and solve for volume. Our moles are going to be 1. The R value that we're going to use is 0.08206. The reason why we chose this particular R value is because we're dealing with the volume and the pressure of the gas. And when you look at the numerator for each of the different R constants, the top one is the one that involves volumes and pressures in terms of liters and atmospheres. We could have, if we're dealing with liters and torr, we would have used the bottom one. If we were dealing with meters cubed and pascals, we would have used the second to last one. Our temperature is going to be exactly 273.15 Kelvin. Standard temperature for gases is at 0 degrees Celsius, but we need this to be in Kelvin. Our pressure is going to be 1 atmosphere. That's the pressure at STP. When we solve for this, we get 22.4 liters. And it turns out that any ideal gas at STP is going to have a volume of 22.4 liters. That value you can actually find on your data sheet. That's it for this video. Thanks for watching. Have a great day.